As we discuss linear optimization models, there's one nuance that we have to include in our discussion, and that's around using integer linear programming for certain problems that we're going to face. So let's talk about what that nuance really means. Integer linear programs are problems that are modeled as linear programs with the additional requirement that one of the variables or more of the variables must be an integer. So when we think about discrete numbers or discrete problems versus continuous problems, these problems we're now talking about are discrete problems that we're now going to solve. The objective is to provide an applications-oriented introduction to integer linear programming. What types of optimization models are we going to deal with if we're dealing with integers? Here's a couple. We have the all-integer linear program that we could build, which is if all variables are required to be an integer. We could do a mixed integer linear program. In sum, that might mean that not necessarily all the variables are required to be an integer. We have the binary integer linear program, where integer values and variables may take on only the value of 0 or 1. That would be of interest to a lot of our engineers and computer science people out there. And then the last one is the LP relaxation, which is the linear programming relaxation of the integer linear program. What that basically means is that the program that results from dropping the integer requirement is the result, and that's the thing that you're going to be looking at. As we talk about this, I think it makes sense to really use an example. So let's use the example of the Eastborne Realty, which is going to be an example of how we look at this nuance of having an integer optimization problem. Eastborne Realty has $2 billion available for purchase of new rental property. So for all of you real estate people out there, this is going to be something that you can identify with. After an initial screening, Eastborne reduced the investment alternatives to townhomes and apartment buildings. So those are the two options in purchasing real estate. Each townhouse can be purchased for $282,000. 5 are available. Each apartment building can be purchased for $400,000. The developer will construct as many buildings as Eastborne wants to purchase. Sounds like a good deal, right? Eastborne's property manager can devote up to 140 hours per month to these new properties. So we're starting to hear what the constraints are. Each townhouse is expected to require 4 hours per month. Each apartment building is expected to require 40 hours per month of the property manager's time. So you've got a set capacity of his time that you need to spread across both sets of properties. Let's talk about annual cash flow. The cash flow per townhouse is expected to be $10,000. The cash flow per apartment building is expected to be $15,000. And that's after deducting mortgage payments and operating expenses. Eastborne's owner would like to determine the number of townhomes and the number of apartment buildings to purchase to maximize annual cash flow. So you're starting to hear what the objective function is, and you're starting to understand what the constraints are. Let's define our decision variables. T, we're going to use to represent townhomes, makes sense. And A, we're going to use to represent apartment buildings. Now that we know what our decision variables are, we can put together our objective function. That is to maximize 10T plus 15A. We have 3 constraints that must be satisfied. First, we have to look at 282T plus 400A has to be less than or equal to 2,000. You may be looking at that and say, well, where did that come from? Basically, we're saying that the price for the townhomes, $282,000, plus the price of the apartment buildings, $400,000, both of those together, depending on the number that we produce, has to be less than or equal to 2 million. Those numbers are represented in thousands. Now we have the manager's time constraint that we have to put in there. 4T plus 40A has to be less than 140. So he only has 140 hours to provide maintenance for these buildings. The townhomes takes 4 hours, and the apartment building takes 40. So those together, depending on the amount that you produce, has to be less than his available time of 140. The last constraint is related to the availability of townhomes. So T has to be less than or equal to 5, because there are 5 townhomes available. One other constraint we have is that the variables T and A must be non-negative. We can't buy -1 townhomes or -1 apartment buildings. That won't work. And in addition, the purchase of the fractional number of townhomes and or a fractional number of apartment buildings is unacceptable. That's the nuance that we have to now address when we start dealing with integer linear programming. You can't buy half of a townhome. You can't buy 0.65 of an apartment building like we could before. Now you have to buy whole discrete buildings. How does that nuance now change how we solve the problem? Now that we have the model for the problem, we realize that this is what we would call a linear, all integer program to solve, because each townhome has to be a whole unit, each apartment building has to be a whole unit. If you look at figure 9.1, you will see each of the constraints plotted on a chart. We talked about earlier this idea of a feasibility region. So you start to see the feasible region where each of the solutions in that region would solve the constraints. Remember, our objective is to maximize the amount of properties we can buy based on the budget we have. However, this problem is different because we have to choose integers. We have to choose whole numbers. As you see there, the objective function now has to not only pass through the feasibility region, or the feasible region as we call it, it also has to strike one of the whole integer numbers of apartment buildings and townhomes. The optimal integer solution, as we see here, is where T is equal to 4 and A is equal to 2. The objective function now is equal to 70. That line, as you see on this graph, goes through that point of T equals 4 and A equals 2. We can't go beyond that point because we have no amount of apartment buildings and no amount of townhomes in whole numbers that would solve the objective function. So point B, the intersection of the manager's time constraint and available funds constraint, that is where T equals 2.4 and A is equal to 3.252. We know that won't work, even though that's the optimal solution based on the feasible region. Why won't it work? Because we need integers. We can't sell or buy 2.479 townhomes. We can't sell or buy 3.252 apartment buildings. It has to be a whole number. Now, if we could do that, then the optimal cash flow would be $73,574. Unfortunately, we can't buy fractional townhomes and apartment buildings. So we have to do further analysis. In many cases, a non-integer solution can be rounded to obtain an acceptable integer solution. As we learned to round numbers when we were in middle school and elementary school, or even high school when we did math, we always rounded those numbers up. However, as we learned when we were doing regression analysis, anytime you're making an estimate of a number versus its actual number, there's error involved. In this case, because we're doing integer linear programming, the error that would be involved by rounding up or down could make sure that you don't have the optimal solution. So with that, there's something different that we're going to do. The optimal solution, if we relax all of the constraints as it relates to integer linear programming, would be townhomes equal to 2.479 and apartment buildings equal to 3.252 apartment buildings. So if we rounded it, we expect to have a substantial economic impact. Suppose we round the solution using this process, and we use 2 townhomes, and we use 3 apartment buildings. We put that into our objective function. We have 10 times 2 plus 15 times 3 is equal to 65. The annual cash flow of $65,000 is substantially less than the annual cash flow of $73,574 based on the optimal solution. So what do? We have to test other possibilities in the feasible region. One we could test is if we buy 3 townhomes and we use 3 apartment buildings. When we plug those numbers into our objective function, we end up with $3,738,000. We only have $2 million to spend, so we know that's not feasible at all. So the rounded solution we're going to go with is T equals 2 and A equals 4. Well, if we use that, we know that's infeasible for the same reason, because we don't have enough money to buy 2 townhomes and 4 apartment buildings. When we round these different numbers off for our variables that we're looking at, it becomes a trial and error approach. Each rounded solution must be evaluated for feasibility as well as its impact on the value of the objective function. Even when a rounded solution is feasible, there's no guarantee that the optimal integer solution has been found. To summarize this section, when we're doing integer linear programming, there's more trial and error involved as opposed to doing continuous linear programming like we've done before. You have to continue to test different solutions that are integers for both decision variables and make sure that the outcome fits the constraints and maximizes or minimizes your objective function. These problems are hard to solve at first, but they become easier with practice. So continue to practice finding those solutions and testing your function to make sure that all of your constraints are met.